What I want to do now is to move on and look at something known as Goodnessoffit statistics. Now, the idea of Goodnessoffit statistics is that we can get an idea of how good each of the explanatory variables are individually by looking at their t-ratios. If the t-ratios are large in absolute value, that means that the particular variable associated with that has a strong explanatory power for the dependent variable that we're trying to model y. But what about if we're interested in measuring how good our set of variables is taken altogether or taken as a whole? In other words, what we want is some measure of how well the sample regression function actually fits the data. And the quantity that gives us that measure is known as the Goodnessoffit statistics. So Goodnessoffit statistics measure how well a sample regression function fits the data. Notice once again that ideally we would have liked to know how well the sample regression function fits the population regression function. But unfortunately, we never know what the population regression function is, and therefore we can never get an idea of how well the sample regression function approximates it. So all we do is say, given the model that we've got, how well does it fit the data? Well, we've got one kind of Goodnessoffit statistic that we know already, and that is the residual sum of squares. Now, the residual sum of squares does measure the Goodnessoffit because it tells us what the average distance is from the points to the fitted line. And we know, everything else being equal, if the residual sum of squares is small, that means the model fits the data very well. If the residual sum of squares is large, that means the model doesn't fit the data very well, everything else being equal. But unfortunately, we can't really say very more than that because the residual sum of squares doesn't have a nice interpretation. So, for example, we might estimate a regression model and the residual sum of squares might be 1362.4. And we might estimate a different regression model and find that the residual sum of squares is 0.0061, for example. We can't necessarily infer that this is a very good model and this isn't, if the two models are for different dependent variables. The reason is obviously that the residual sum of squares will scale with the data y. So, for example, if we are trying to model some dependent variable y which takes on very large values, for example, we're trying to model the level of gross national product in the UK, then the residual sum of squares from that model will be fairly big. If, on the other hand, we're trying to model something which takes on very small values, for example, half-hourly stock returns, then the scale of those half-hourly stock returns will be fairly small. They'll be quite compact, and therefore the residual sum of squares will also be small. So what we need is some measure a bit like the residual sum of squares for measuring how well the sample regression function fits the data, but one which isn't dependent upon the scale of the data. Now, the very most common Goodnessoffit statistic is known as R-squared. There are several definitions of R-squared that we could use, and the simplest definition is to say that R-squared is the square of the correlation between the actual and fitted values. Now, obviously, if the correlation between the actual and fitted values is relatively high, R-squared will be relatively high, and we would say that the model fits the data fairly well. If, on the other hand, the square of the correlation coefficient between the actual and fitted values is relatively small, that is close to 0, then we know that the regression model doesn't fit the data very well and R-squared will be relatively small. So we can see immediately from that, and it turns out that it's the same if we had other definitions for R-squared. We can see that a bigger R-squared means that the model fits the data relatively better. A smaller R-squared, i.e. close to 0, means the model fits the data relatively poorly. There's another definition of R-squared, however, which is more commonly used than the definition of the square of the correlation coefficient between the actual and fitted values. To see how that other definition works, recall what we're trying to do when we estimate a regression model. Well, what we're trying to do is to find the model that explains the highest proportion possible of the variation of y about its mean value. Well, it should be obvious to you why the model is trying to explain the variation in y. We're trying to say, why does y move about from one observation to another? Well, the answer is y moves about because the explanatory variables in our sample move about. But why are we trying to model the variation in y about its mean value? Well, the answer is the kind of mean value, if you like, provides a kind of benchmark in the sense that if we couldn't think of any explanatory variables to have in our regression model, so that our regression model only included an intercept, yt equals beta 1 plus ut, then it turns out that the estimated value of the intercept in this case, beta 1 hat, would exactly equal the mean of the observations on y. So what we do when we calculate these total variability of y about its mean value, in a sense we're allowing for y to have a non-zero mean. Or equivalently, we're saying that if we couldn't think of any explanatory variables, in a sense the base case, if you like, is where we have a regression model with no explanatory variables, and therefore the intercept would equal the mean value of y. So we can define the total variability of y, the total sum of squares, as being the sum of yt minus y bar squared, added up over all of the observations. Now this quantity, the total sum of squares, could be split into two components. The first component is known as the explained sum of squares, and that is the proportion of the total variability of y which is explained by the model, and another part which is known as the residual sum of squares, and that's the part of the variability of y which is not explained by the model. So we could write total sum of squares equals explained sum of squares plus residual sum of squares. So residual sum of squares, we know that's the sigma u hat t squares. The total sum of squares we've just defined, the total variability of y, that is sigma yt minus y bar squared. What is the explained sum of squares? Well, that's the variation of the weighted values about the mean of y. So that's sigma y hat t minus y bar squared. Once we've defined the total and explained sum of squares in this way, we can define R squared as being the ratio of the explained sum of squares to the total sum of squares. And if we define R squared in this way, we can interpret R squared as saying that it's the proportion of the total variability of y which is explained by the model. So R squared is the proportion of the total variability of y which is explained by the model. But since we know that the total sum of squares equals the explained sum of squares plus the residual sum of squares by construction, we could also say that the explained sum of squares equals the total sum of squares minus the residual sum of squares. So we could substitute into the formula for R squared to substitute out the explained sum of squares. If we did that, we could write R squared equals 1 minus the residual sum of squares divided by the total sum of squares. So there are various ways that we could write it. Now, given that I said earlier, one possible definition of R squared is that it's the square of a correlation coefficient, we know from that definition, and from this other definition I've just spoken about, the same thing follows, we know from that that R squared must lie between 0 and 1. So we could write 0 is less than or equal to R squared is less than or equal to 1. So what we want to do now is to think about what are the implications of R squared taking on values equal to these extremes or limits here. So first of all, what would it be like if R squared took on a value of 0? Well, by our definition of R squared, if it takes on a value of 0, that must mean that the explained sum of squares is 0. In other words, this is the worst possible scenario. The explained sum of squares is 0, and so our model hasn't succeeded in explaining any of the variability of y about its mean value. In other words, the residual sum of squares equals the total sum of squares. Now we could plot what this would look like on a diagram. So if R squared equals 0, our model has failed to explain anything whatsoever. That must mean that the estimated values of all of the slope coefficients are exactly 0. So for the case where R squared equals 0, if we plotted x2t, let's say, against yt, and our regression was just one of yt on an intercept and the single explanatory variable x2t, then r squared corresponding to 0, r squared equaling 0 must correspond to the situation where beta 2 hat exactly equals 0. That would be the case where the estimated line was exactly flat. So this point here, the intercept beta 1 hat would be equal to the mean value of y, and beta 2 hat would be 0. So we'd have a random, we'd have the observations dotted around the fitted line, and the fitted line would have a slope of 0. That's the only situation where r squared would exactly equal 0. We can see immediately that this isn't going to actually apply very often in practice. In fact, we can go further than that and say this will never actually happen in any practical situation. Obviously, it's never going to be the case that the estimated value of beta 2 in practice is exactly 0. Even if the two variables x2 and y were completely unrelated to one another, for example, if x2t were monthly rainfall in China and yt were returns to the London stock market, then those two variables are clearly very unlikely to be related to one another, but if we regressed one on the other, we'd never get an estimated value of the coefficient exactly equal to 0. So the theoretical lower limit of r squared is 0, but in any practical sense, r squared can be very small, but it's never going to be 0. What about the other theoretical limit for r squared? Well, r squared equals 1 is the exactly opposite scenario. R squared equals 1 must, from our definition of r squared, imply that the explained sum of squares equals the total sum of squares. What does that mean? That must mean that the residual sum of squares is 0. In other words, our model has succeeded in explaining every bit of the variability of y about its mean value. If the residual sum of squares is 0, because all of the residuals are squared in the sum, so that the positive and negative ones couldn't cancel each other out because we're squaring them all, that must mean that the residuals themselves are all 0. So if we were to plot r squared equals 1 in the case of the bivariate regression model, so we've got x2t on the x-axis and yt up here on the y-axis, that would correspond to the situation where all of the points lied exactly on the fitted line. So r squared equals 1 means all of the points lie exactly on the fitted line. Once again, that's never likely to happen in practice. We'll never have a situation where the points all lie on a straight line, either in 2 dimensions or in the multiple regression case in many dimensions. We'll never have that. So 0 and 1 exist only as theoretical limits. It's quite common, however, that we get r squared values that are 0.9 or even higher. So r squared is a very nice, simple, intuitive, easy to calculate and easy to understand method for deciding how well the regression model as a whole fits the data. But as with all simple things in econometrics, it has a number of drawbacks. The first of these drawbacks is that by its construction, r squared is defined in terms of the variation of y about its mean value. So that if the model is rearranged in some way, and an econometric word for rearranged is reparameterized, if the model is reparameterized and the dependent variable changes, r squared will also change. So for example, suppose we were comparing between 2 regression models with the same explanatory variables, but different explained variables. Then automatically we get a different value of r squared between those 2 regressions. So if we had some variable called yt that we were trying to explain, let's say we just had one explanatory variable to make it simple, then we use the same explanatory variable, but we try to explain a different variable. Let's call it zt, and let's call that beta 1 dashed and beta 2 dashed x2t plus vt. Then obviously this explanatory variable is the same, but because this variable that we're trying to explain is different, we cannot compare r squareds across the 2 models. So if r squared for this regression was 0.8 and r squared for this second regression was 0.6, let's say, we couldn't say that the first model is better than the second one. All we could say is that the first model better explains the variability of y about its mean value than the second model explains the variability of z about its mean value. We can't make a direct comparison between the two models. More seriously than that, if we take a given model and just rearrange it a little bit, then automatically we'll end up with a different r squared. So for example, let's add one more explanatory variable into the model here. So we've got beta 3 x3t plus ut. If I take this model and just rearrange it, let's suppose that I subtract x3t away from both sides of this expression, then what have we got? We'd have yt minus x3t on the left-hand side equals beta 1 plus beta 2 x2t plus, how many x3t's have we got? Well, we had beta 3 x3t and we've subtracted an x3t from both sides. So if we factorise it, we'll have beta 3 minus 1 times x3t plus ut. You can see that this second model is simply what we call a reparameterisation or rearrangement of the first. Now, clearly, if the models are essentially the same, one is just a simple rearrangement of the other, then the two models will have identical values of the residual sum of squares. However, because of the way that we've defined r squared, the two models will have different values of r squared in general. The reason is that we defined r squared in terms of the variability of y about its mean value. That was the total sum of squares, which is incorporated in the r squared formula. So in the first case here, we're measuring the total variability of y about its mean value. In the second case, we're measuring the total variability of yt minus x3t about its mean value. So you can clearly see that in these two cases, the total sum of squares will be different from one regression to another, and therefore the value of r squared will also be different. And that's clearly very unfortunate. And means that it's difficult to compare between models with different explained variables, even if the explanatory variables are the same. The second problem is that the value of r squared never falls if we add more explanatory variables into a regression. So let's suppose that we've got two regression models. The first one has two explanatory variables, x2 and x3, plus we allow for an intercept term in the model. The second regression is identical to the first, but also has an additional explanatory variable x4. Now what we'd like is a Goodnessoffit measure that allowed us to choose one of these two models that best fits the data. Well, it turns out that if we denote the value of r squared for the first of these regressions by r1 squared, and the value of r squared for the second of these two regressions by r2 squared will always be at least as big as r1 squared. So r squared will never fall if we add an extra explanatory variable into the regression model. Now, if we think about why that happens, well, the answer is obviously in both cases the dependent variable y is the same, so the total sum of squares will be the same. But on the other hand, if we add an extra explanatory variable in the model, unless the estimated value of beta 4 is exactly equal to 0, then the residual sum of squares for the second model will be lower than the first. So if the residual sum of squares falls from the first model to the second, then the value of r squared must go up by definition. Under what circumstances would r1 squared exactly equal r2 squared? Well, I've just suggested that already. That would happen if and only if the value of the estimated parameter on this new variable, beta 4 hat, was exactly equal to 0. Then the residual sum of squares for the first regression would exactly equal the residual sum of squares for the second one. In that case, the r squared will be exactly the same. Once again, even if explanatory variable x4 was completely irrelevant, in practice this is never going to happen. So that being the case, in practice, the value of r squared will always be bigger if we add more explanatory variables in. So what's the upshot of that? Well, the upshot is that we cannot compare between regression models which have different numbers of explanatory variables. The final criticism of R-squared is that in practice, especially for time series regressions, it often takes on very high values within a narrow range. So for time series regressions, R-squared often takes on a value of 0.9 or greater. So for example, we might have one regression where R-squared takes on a value of 0.96 and another regression where R-squared takes on a value of 0.97. So even if the dependent variables for these two were the same and the number of explanatory variables were the same in these two cases, so we could legitimately compare between them, even in that case, these values are so very close together that it's hard to distinguish them. And unfortunately, this often happens in practice. So we could say that R-squared doesn't provide a very sharp characterization of how well the model fits the data. Often R-squared takes on values within a very high narrow range. So it's hard to choose between them. So I've noted here 3 problems with R-squared as a Goodnessoffit criterion. We're stuck with the first and third of these problems. There's not very much we can do about them. We'd have to throw this whole philosophy of measuring Goodnessoffit away and use some other approach entirely. We can, however, get around, at least in part, the problem that R-squared always increases if we increase the number of explanatory variables. And the way that we do that is to define a modified version of R-squared. Now, this modified version of R-squared is sometimes called adjusted R-squared, or sometimes it's called R bar squared, because we put a bar over the letter R. So what's the difference between R bar squared, adjusted R squared that is, and the original R squared? Well, the answer is the formula for adjusted R squared, if you look at it, includes the original R squared, so it's a function of R squared, but it also incorporates an extra set of terms. And those extra set of terms implicitly incorporates a penalty which allows for the problem that when we increase the number of explanatory variables, we use up degrees of freedom. So it's a penalty, if you like, for increasing extra explanatory variables. So if we add another explanatory variable into a regression model, for example, moving from regression 1 to regression 2 on the previous slide, then 2 things will happen in the formula for adjusted R squared. The first is we know that in practice R squared will always rise. The second thing is that the penalty term will increase because the value of k, the number of explanatory variables including an intercept, has increased. Therefore, this will have an offsetting impact on the value of adjusted R squared. So R squared always goes up when we add more explanatory variables in. The impact on the penalty term is such that the penalty term would lead adjusted R squared to 4. So when we add explanatory variables to the model, we can't immediately say what the impact on adjusted R squared would be. If we add a very important explanatory variable, then the increase in R squared will be enough to offset the impact of the penalty term, and therefore adjusted R squared will go up. If, on the other hand, we add in a variable that's irrelevant and statistically insignificant, then even though R squared goes up, it doesn't go up by enough to offset the impact of the increase in the penalty term, so that overall, when we add this additional explanatory variable, adjusted R squared will fall. So adjusted R squared is better than R squared in the sense that it does allow us some method for comparing between models with different numbers of explanatory variables. Now, unfortunately, there are still problems with adjusted R squared as a criterion for comparing between models and for deciding how many explanatory variables to include in a model. Now, if we're trying to decide how many variables from a set of candidate variables to include in the model, we could follow the rule, I will add this extra explanatory variable to my model if it leads the value of adjusted R squared to rise. But if we do that, it turns out that adjusted R squared is a very soft rule for deciding whether to include other explanatory variables or not. Now, for the sample sizes that are of relevance in finance, the number of observations t is likely to be very large. And you can see, if you look at the formula for adjusted R-squared, that asymptotically, that is, as the sample size tends to infinity, the value of adjusted R-squared will converge upon the value of R-squared. So, if we have enough observations, then the penalty term hardly bites at all. So when we add another explanatory variable into a model where we had lots of observations, then almost certainly adjusted R-squared will go up, even if that explanatory variable was very, very insignificant in the regression. Secondly, what we'd like is some statistical measure to tell between different values of R-squared or different values of adjusted R-squared. So if, for example, we wanted to compare between these two situations here, where R-squared equals 0.6 and R-squared equals 0.7, we'd like to be able to do that in a statistical sense. So statistically, are these two a long way away from one another? Well, unfortunately, since we don't have a statistical distribution for R-squared or adjusted R-squared, in other words, because R-squared doesn't follow a t distribution or an f distribution, or in fact any distribution at all, then we can't make statistical quantitative comparisons between R-squareds. All we can do is say, well, this value of R-squared is bigger than this one, so therefore, if the caveats that I spoke about earlier don't apply, then this value of R-squared is bigger and therefore this model fits the data better. That's all we can say. We can't say whether this model here fits the data statistically significantly better than this one. We can just say that the R-squared has gone up slightly. So all we can do is look at the value of R-squared and say whether we like it or not.